Hello, for this problem we've got a small off-road trailer that we're going to approximate as a rectangular prism. That's the silver part here. That's got a 100 kilogram mass supported by two 25 kilogram wheels. The wheels we're going to approximate as a slight, thin circular disc with a mass of 25 kilograms and a diameter of 60 centimeters. Assuming that the wheels roll without slipping, we're asked to determine what power is required to bring the trailer from rest to a speed of 80 kilometers per hour over the course of 10 seconds. So the first thing we're going to be doing in here is we are going to need to modify some of these. So 80 kilometers per hour, so V final is 80 kph. We're going to convert that into meters per second just to make our lives a little bit easier. So if we do that conversion, we're going to find that the velocity final is 22.22 meters per second. We're also going to look at the angular velocity. So if the trailer itself is moving 22.22 meters per second, how fast are the wheels rotating? So for that, it is rolling without slipping, which means that V equals negative R omega. The V is the velocity of the trailer, and that's going to be the same as the velocity of the center of the wheel. R is the radius of our wheels. So if it's a 60 centimeter diameter, it's going to be a 30 centimeter or 0.3 meter radius, which means that my omega is going to be negative 74.07 radians per second. All right, so that's some of the prep work. The main equation here is going to be related to power. So P, or power, is equal to work done over time, which in this case is going to be equal to the change in kinetic energy over time. So delta KE, I'm going to have two components to this. So I've got translational and rotational motion. So for the translational part, I'm going to have 1/2 mv final squared, and for the rotational part, I'm going to have 2 times 1/2 I omega final squared. So I've got, this is going to include the mass of everything that's moving, wheels and trailer, and I've got two wheels that are both rotating. That's the final minus initial, so minus 1/2 mv initial squared plus 2 times 1/2 I omega final squared, or sorry, initial. Let me fix that. All right, and all of this gets divided by time for the power part of this. So I do have, starting from rest, so this is all 0. So let's go ahead and I kind of simplify this, put some numbers in. So the power is going to be equal to 1/2, and for the mass, I need to include the mass of everything. So I've got 100 kilograms for the silver box part, and then 50 kilograms of wheels. So 150 kilograms total for the mass that is moving at 22.22 meters per second. V final is, again, that 22.22 meters per second squared. And then I've also got the rotational part. So 2 times 1/2 times I. So for a thin circular disc, I is 1/2 times mass of 25 kilograms times omega final, negative 74.07 radians per second squared. So, and then omega final, oh, oops, I messed this up. Sorry, I got ahead of myself with this. So I is 1/2 mass times a radius, so 0.3 meters squared, and then omega final is negative 74.07 radians per second squared. So this right here is my I. And then all of this gets divided by my 10 seconds for the whole thing to take off. So if I plug all these numbers into my calculator, solve for everything, I'm going to get a final power, required power of 4320.2, and kilograms, meters, seconds. All of this is going to work out to be watts. So if I want to put this into more convenient units, so if this were an electric car, it'd be about 4.32 kilowatts for the required power. If this was an internal combustion engine, it would be about 5.79 horsepower is required to get this trailer up to speed. All right, so that's all we have for this example. Thank you for watching and hope to see you again.